All right, so now we're going to see how Galerkin variational integrators induce symplectic partition Runge-Kutta methods in some instances. So Galerkin variational integrators. And sort of SPRK methods. Okay, so let me state a theorem. Okay, so if you're given a set of quadrature points, let's call them C1 to CS. Okay. With the corresponding maximal order weights. Let's call it BI. Okay, so the maximal order weights really just come from integrating the Lagrange polynomial associated with these quadrature points C1 to CS. It's like from the interval from 0 to 1, right? Okay, so so this is really just the integral from 0 to 1 of the Lagrange polynomial of the ith Lagrange polynomial. It's like S and then tau d tau. Okay. Okay. And then sort of where this Lagrange polynomial LIS has the property that when you evaluate it at the point Cj, this is the Kronecker delta function, delta ij. Okay. All right. Okay. Now you let LD, right, be the corresponding Galerkin discrete Lagrangian. Okay, then the claim is that the integrator generated by the discrete Lagrangian is a partitioned, is a symplectic partition Runge-Kutta method. Sort of defined by the following coefficients. All right. So we already know what the BI's are. BI equals to BI tilde, okay, equals to the integral from 0 to 1 of this Lagrange polynomial LIS tau d tau. Okay, well, I guess in the paper it uses rho, so let me just change all of this to rho. All right, and then the AIJs, okay, are what you typically expect. It's the integral, instead of from 0 to 1, 0 to Ci of LJS rho d rho, okay, and then the AIJ tilde is equal to BJ tilde 1 minus AIJ over BI. Okay, so if you know something about symplectic partition Runge-Kutta methods, then you know that there are sort of two conditions for symplecticity. All right, so maybe maybe I should write that down. So the two conditions are that exactly bi is equal to bi tilde, and the other condition is that bi aij tilde, right, plus b tilde j a I j. Okay, let me just check this. Yeah, so this is AJ, I'm sorry. Yeah, that didn't look right. Okay, so this is HAI. Okay, is equal to bi bj tilde. Okay, yeah, so those are the two conditions, if you will. It's like for a partition Runge-Kutta method to be symplectic. And you can sort of see that these hold. It's like because you have this part here, and then of course this condition here also guarantees is equivalent to the second one, right? So it's nothing more else. It's like if you just solve this second equality for aij tilde, it's like you get exactly this condition here. Okay, so all right, so that's what happens. Okay, and then of course, as I said, it's like the LIS. It's like is the Lagrange polynomial basically associated with the quadrature points, and it satisfies this Kronecker delta property. All right, so that's perhaps not so surprising. It's like, but let's just see that is indeed the case. So I will copy these conditions into a corner somewhere, and then we'll prove this result. Okay. So we have that bi equals to bi tilde equals the integral from 0 to 1 of lis rho d rho. aij equals to the integral from 0 to ci ljs rho d rho. And then aij tilde equals to bj tilde 1 minus aji over bi. Okay, all right. So those are the coefficients of the Runge-Kutta method based on having quadrature points and these maximal order quadrature weights. Okay, so let's try to prove this now. Okay. Okay, so let's say you're given Q0, P0, Q1, P1, and let's see, Q0 nu, okay, satisfying the conditions. It's like which are associated with the sort of Hamiltonian map for the Galerkin variational integrator. So let me just actually write those down. Okay, so there's this minus P0 equals to H sum from I equals to 1 to S bi dl dq cih L tilde 0s ci. Okay, so the reason, of course, why you have two different Lagrange polynomials is because the L Lagrange polynomials are associated with the quadrature points C1 to Cs. And if you recall, the L tilde Lagrange polynomials are associated with some sort of control points, all right? Which parameterize, it's like the space of sort of polynomials of degree S satisfying the boundary conditions. Okay, so okay, plus 1 over h dl dq dot, okay, CIH L tilde dot 0s CI. It's one equation, and then there are a bunch of s minus 1 of these. Which looks very similar, except that instead of 0, you have a new s. And then there's a P1. All right, so these are the equations which define the symplectic map. It's like from Q0, P0 to Q1, P1, okay, which come from this Galerkin variational integrator. So we want to show that that's equivalent, it's like, to this symplectic partition Kuda method with these coefficients, okay. All right, so, and so I'm going to consider the partitioned Kuda method. Okay, so this looks like Q1 equals to Q0 plus H, sum from J equals 1 to S of Bi Q J dot, sorry, Bj Qj dot. Right, then there's P1 is equal to P0 plus H, sum from J equals 1 to S of Bj tilde, Pj dot. Those are the updates, and then you have to define what the internal stage values are. Qi is equal to Q0 plus H, sum from J equals to 1 to S of, Aij. Aij Qj dot, and then Pj is equal to P0 plus H, sum from J equals 1 to S of Aij tilde Pj dot. Okay, and then you have to write down what the vector fields are. Pi is equal to dl dq dot at qi and qi dot. And as was the case before, you should think of this as implicitly defining for you what qi dot is in terms of qi and pi, and that's always possible if the Lagrangian is regular, which is to say that the Legendre transform is invertible. Okay, and then pi dot is equal to just dl dq at q and qi dot. Okay, and then here, again, I is from 1 to S. I is from 1 to S. Okay, so let's see what happens, all right? So let's, in particular, consider a curve, a polynomial, which has the qi dots as the derivatives at the quadrature points, right? So you let qi dot be equal to qd, right, at CIH, and then this QD implicitly depends on the control points and the time step H. Okay, so this implies that QD, well, should put the dot derivative of it, right? So QD dot of tau h q0. Okay, so this derivative is equal to okay, the sum from j equals 1 to s of qj dot times the Lagrange sort of polynomial, okay, j comma s tau. Okay, so given this, it's like what you can do, of course, is you can integrate this. Okay, so I can integrate sort of this equation to obtain the following. So here you use the initial condition, right? So qd tau h, depending on these parameters, okay, is equal to q0, which is the initial value, right, plus h times the sum from j equals 1 to s q j dot, the integral from 0 to tau of lj ljs rho d rho. Okay. So you can let the QIs now be equal to this QD at CIH, again with these parameters. Okay. Right. Okay. And in particular, right, Q1 is equal to QD at tau, sorry, at H, I'm sorry, that's what I wanted to say, at H of this thing, okay, which by this equation is Q0 plus H, the sum from j equals 1 to s of qj dot, the integral from 0 to 1 of ljs rho d rho. But this, of course, is nothing more than the bj coefficient. Okay, so this is bj. So this condition is exactly this very first equation here. Okay, so we've gotten that. Okay. So what's the strategy here, right? The strategy basically is to show that if you have a solution that's like associated with the Galerkin variational integrator, you can use that, it's like to construct, you know, the internal stage values in such a way that, you know, both everything sort of satisfies this system of equations instead, right? So the first thing we've seen, it's like starting from these conditions, is that Q1 actually satisfies the equation you want here. Okay. Now you impose these conditions, right? So if you know what QI and QI dot are, okay, you can then use these equations. You can impose this. Okay, so we have this. We sort of impose these. And we're trying to sort of show the rest of it. Okay. All right. So what we're going to take advantage of is this condition here, the one in the middle, right, which holds for I equals 1 to s minus 1. Actually, we have not made use of any of the relations here so far. So let's see what happens, okay? All right, let's see now. So now we make use of relations. So basically what I'm going to do is that, there were s plus one of those equations. We're going to actually add all of them up, okay, by adding all of them together. And if you recall, it's like on the left-hand side of the equations, there was a minus p0, there were a bunch of zeros, and then there was a p1, right? So if I sum all of them up on the left-hand side, I get p1 minus p0, and on the right-hand side, I get now I'm going to do a double sum, okay? So I'm going to write h times the sum from I equals 1 to s of bi, and then was this dl dq cih term, and then a bunch of Lagrange polynomials, right? So there's a sum from nu equals to 0 to s of the Lagrange polynomials, L tilde, it's like nu s, okay, ci, okay, plus 1 over h dl dq dot at cih, the sum again from nu equals to 0 to s of L tilde dot nu s ci. So one thing it's like you should probably know, and you probably know, is that this thing here, right? So one way to think about this is that this is the interpolating polynomial corresponding to something which takes values 1 at all the CIs. Okay, so and in particular, it's like the constant function 1, right, will be exactly interpolated because it's a polynomial of degree 0, and the corresponding interpolating polynomial is exactly the sum. So this really is just 1, okay? It's just 1, identically 1, okay? And then given that observation, then this thing, which involves the sum of the derivatives of the Lagrange polynomials, has to be 0. Okay, so then this here is 0. Okay, so you're just left with h, the sum from I equals 1 to s of bi dl dq cih. Okay, but dl dq cih is just pi dot. Okay, so that's equal to h, the sum from I equals 1 to s of bi pi dot. Okay, so this is telling you that P1, so this implies that P1 is equal to P0 plus h, the sum from, I'm just going to reindex it, so j equals to 1 to s of bj pj dot, which, and since, it's like, right, and we already used the fact that bj had that form, so this is just going to be bj tilde, right? bj is equal to pj tilde. So this condition means that this equation is satisfied. Okay, so we're just left with the internal stage conditions. Okay. I should also say that, these internal stage conditions for the position just come from doing something similar to this, right? That the QIs are QD at the internal stage values, which is what I said here. But you can then obtain them by this integration. But instead of having 0 to 1, you have 0 to CI. Okay, and then that gives you the AIJ coefficients. So, so this, if you will, just comes from the fact that Qi is equal to Qd CIH, right, which is Q0 plus H, the sum from j equals 1 to S of Qj dot, the integral from 0 to Ci L Js rho d rho, okay, right, but that's of course Aij, which this is Aij, so this is equal to Q0 plus H, the sum from j equals 1 to S Aij Qj dot, okay, so that gives you this condition. So the only thing we have left to worry about is this condition here. Okay, all right, so let me copy that down here and then we'll try to finish up the rest. Okay, so the only thing left to show is that Pj has this relationship. Pj is equal to P0 plus H sum from j equals 1 to S of Aij tilde Pj dot. Okay, yeah, so we showed these conditions as well. So we just need to have this final relationship for Aij tilde. Okay. All right, so let's see. Okay, so now we have to use some sort of relationship between the two types of Lagrange polynomials. Okay, so so these L tilde nu S plus 1, right, is a set of S plus 1 independent polynomials. Of degree S. So it's a basis for polynomials of degree S. Okay, so for each j equals 1 to S, okay, this polynomial LJS, right, is of degree S minus 1. Okay. And if you're asking why it's of degree S minus 1, it's because it's the Lagrange polynomials associated with quadrature points from 1 to S. They're S quadrature points, so you know that they're only S degrees of freedom, so that corresponds to a polynomial degree S minus 1, right? And so its integral is of degree S. Okay, so what that implies is that there's some way to write relate the integral, it's like of you know, these Lagrange polynomials and expand it, it's like in this L tilde basis, if you will. So this implies that there exists coefficients let's call them M nu J such that the sum over nu from 0 to S Okay. Okay. New s plus 1 tau dot, well, no dot. Okay. Okay, so some linear combination, it's like of these basis functions is equal to the integral from 0 to tau of the Lagrange polynomials. Okay, LJS tau rho d rho. And then I can put a minus bj there, right? Okay. All right. So if I differentiate this, with respect to tau, and you evaluate at tau equals to 0, right? Then, and tau equals 1, then what you get is that the sum from nu equals 0 to s of m nu j, it's like L tilde dot nu s plus 1 tau is equal to L js tau. Okay, all right, so this is differentiating it. Now I want to evaluate it at tau equals to 0 and tau equals to s. Okay, so m sj is equal to the sum from nu equals to 0 to s of m nu j L tilde nu s plus 1 at 1. All right, so so I'm just using this Kronecker delta property, if you will. It's like of this Lagrange polynomial. Okay, so all of them will vanish except for the one associated with the last endpoint. Okay, so this is equal from integral from 0 to 1 of LJS rho d rho minus bj. But that's equal to 0 because that integral is equal to bj, yeah? Equals to 0. Okay, so j is equal to 0, and then m0j is equal to the sum and that's equal to this integral minus bj. So the integral from 0 to 0 is 0, so you just get minus bj. Right? Okay. All right, so anyway, so that's some sort of combination. So if you look at the relationships, it's like in the discrete Hamiltonian map for the Galerkin variational integrator, and you number them from 0 to s, right? And you weigh it with these weights, then what will happen is the following. Okay, so I'm going to take the following sum. Okay, so there was all right. So I should probably have labeled those equations, but if you would label those equations as E new, then what I want to consider, and these equations where if you recall the minus P0 is equal to stuff, 0 is equal to things, this is for new equals to 1 to S, and then there was a P1 equals to something, right? All right, so this is what I mean by the E news, okay. All right, okay. So if I take, oh, sorry, this is 2s minus 1, right? So if I take some weighted combination of these equations, so I consider, and the weights are given by these coefficients, sum from nu equals to 0 to s of m nu j e nu. Okay. What you get is that okay. So I wanted to know what those values were at the extremal points, because on the left-hand side, right, the only non-zero values of a nu equals to 0 and nu equals to s. All right. So this thing means that the left-hand side of the equation corresponds to bj p0, right? So you get bj p0 is equal to something, which is this linear combination. So h sum from I equals 1 to s of bi, okay. And then we use, it's like the fact that you know, the dl dq's, it's like the dl dq dots are related to the p's and p dots, okay. So this is pi dot, and then the weight, okay, so this weight is multiplied into this sort of Lagrange polynomial, right? But it has this form in terms of the integral, right? So let's write that with the integral. So it's an integral from 0 to ci L js rho d rho minus bj. Okay, so, and the reason why you could do that is because if you recall, this piece here, right, is the dl dq at CIH. And this part here, right, is because I have those weights, right? So this is m nu j times, well, there's a sum actually, I guess, is what should be happening. Sum nu equals 0 to s of m nu j L tilde nu s. Plus 1 tau. All right, no, it's not a tau, it's ci, right? Okay, so that's more or less, it's like what's happening is that this piece got replaced with the, well, the piece which comes from taking this weighted combination got replaced with p dot, and then the weighted sum, it's like got replaced with this integral here, okay? All right, and then something similar happens to the other piece. You get 1 over h pi, and then that is just L JS at CI. And then this, of course, comes from the fact that we had this relationship involving the derivatives, right? So this is the derivative, well, the sum, the weighted sum of these L tilde dots is exactly this thing here. Okay, all right. So yeah, so this piece here is the dl dq dot term. And then this piece here is just this, right? The sum from nu equals 0 to s of m nu j L tilde dot nu s plus 1 ci. Okay. All right. So what happens? Okay. So when the dust settles, what you end up getting is the following. Okay, so let's try to recap. You have bj p0 is equal to this thing here, okay? But this, of course, is aij, right? So h, the sum from I equals 1 to s. Okay, I'm going to put the bi in, okay? So you have pi dot bi multiplied into aij minus bj. Okay, so far so good. Okay, and then you have this stuff here. Okay, so here, if you think about it, right, when you sum from I equals 1 to s over, again, these Lagrange polynomials, you have the property that they sum up to 1. Okay, and then there's this h term here. Right. Let me see now. I'm sorry, that's not what happens, right? So what happens is that you have Lagrange polynomial LJS evaluated at CI. It is it has this Kronecker delta property. So the only non-zero term it's like associated with that is when I is equal to j. So what you're just left with is h bj pj times 1 over h, right? So so let me just put a bracket here plus h, right, bj 1 over h pj. So that cancels out. You get bj pj. Okay, so I can reorder this. Okay, so what I want is that pj is equal to p0. So I'm going to divide by bj throughout. P0 plus h, the sum from I equals 1 to s of pi dot, right, bi aij minus bj divided by bj. Okay, all right, and then what I have to do is that I have to, all right, so I'm sorry, you have to swap the order because that's a minus sign, right? So you have bj minus aij, right? But then usually it's like the form, so this is the internal, almost the internal stage equation, right? Yes. Okay. So this is actually pi, I'm sorry. Okay, so I have to reorder, I have to reindex it, so I'm going to swap the i's and j's. So this gives me pi is equal to p0 plus h, the sum from j equals 1 to s of pj dot, and then this is bj bi minus aji divided by bi. Right, so this of course is nothing more than the aij tilde coefficient, right? So this thing here, maybe let's use a different color. So this thing here is aij tilde. Okay, so let's simplify it a bit to see that's exactly that, right? So this is bj, but bj is equal to bj tilde, so I can put a tilde there, divide, and then divided by bi gives me 1 minus aji over bi, which is exactly what we have there, right? So, all right, so what you basically find then is that you know, when you have this Galerkin variational integrator and you look at the discrete Hamiltonian map associated with that, you can reframe everything. You can show that, you know, the solution you get of 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 show up in the sort of discrete Hamiltonian map, right? You end up getting all the conditions. It's like for a symplectic partition Kuta method, right, falling out, and all these relationships automatically hold. So yeah, so that was a little bit of work, but again, now you have this nice observation that you know, the symplectic partition Kuta methods, you know, some subclass of them can be obtained from this Galerkin variational integrator perspective. So let me just stop here.